And now we're going to look at 6.10, compare scores. Our goal, compare data sets and raw scores using standard scores. Let's start with a recap. You've seen this graph before. You have a handout for it. Now it's time to answer a few questions to make sure you understand it. 1, do the percentages on this graph ever change? You see percentages all over the place. Do any of them change? No, never. That's the nice thing about it. It really is useful in helping solve normal distribution problems. 2, when given a problem, what's the first value we always label? That's going to be the mean. Remember, everything is based off of the mean. So, for example, let's say the mean is 100. What do we need to know to find out the next value here, or here, or here? Any of these values. How do we find them out? Well, we need to know the standard deviation, right? So 1 standard deviation to the right is here, 2, 3, and we also have standard deviations that go in the negative direction, right? So let's say the standard deviation was 10. You know you're going to add 10 on every vertical line you go to the right and subtract 10 on every vertical line you move to the left. So a score of 120, for example, would be 2 standard deviations away from the mean, and that's also a z-score of 2. Now, what is a z-score if you had to define it? I would say it's a score that shows you how you compare to others. So if the average is a z-score of, for example, 0, and your z-score was 2, that quickly tells people, compared to others, you did really well. You did better than most. Here's another recap. You can read through this to refresh your memory if you'd like, but I just have one question for you. When we look at these z-scores, are these the only possible z-scores we can ever get? Well, hopefully you remember that this goes a little bit above 3, and this goes a little below -3. We're never touching 4 or 5 or anything like that. It just goes slightly beyond negative and +3. But you can have decimals, remember. So z-scores of, let's say, -1.1, that exists, or 0.5, or 2.3. These are all z-scores you can get, or -3.1. Decimals are possible. Now, let's refresh our memories with one more thing, and that's how to use the z-score formula to answer a question, and then we'll compare some scores. Suppose that the ages of cars driven by employees at a company are normally distributed. So that tells us we can use this graph with a mean of 8 years and a standard deviation of 3.2 years. What's the z-score of a car that is 9.1 years old? You'll need a calculator to work this out in the end, but not right now. My question to you right now is, what does 9.1 represent? The raw score. And which one of these symbols represents the raw score? That's going to be X. X is the raw score. You need to know that for sure. Now, do you remember what this symbol stands for? In the denominator. That is standard deviation. you don't remember that, label that too. I'll just put SD for now. Okay, standard deviation was 3.2, and then the last symbol here, that's the mean, aka the average, they told us, is 8. Now, looking at this formula, there's something you can identify about the z-score right now. Do you know what it is? That it's going to be positive. This score is above average. How do we know? Because the current score is greater than the average, the mean. So we get 1.1 over 3.2. This is where you need your calculator. You'll find the answer is B. Well, let's think about this logically to make sure you fully understand. What if your score was equal, or in this case, the years of the car, but what if the raw score is equal to the mean? What's that going to be? A z-score of 0, meaning your score was the same as the mean, meaning you are perfectly average z-score of 0. Makes sense, right? But what if your score is less than the average? Well, you already know you're going to have a negative z-score. This will be below average. Now that we understand that a little bit better, let's compare some scores, shall we? Z-scores are useful not only for finding how a raw score compares to its own distribution, but also for comparing raw scores from two different distributions. For example, here's the normal distribution of watermelons, where we're comparing watermelons that are average and also below and above average in size. And here is a different normal distribution of strawberries doing exactly the same thing. Now, what we're going to do is compare these normal distributions to each other. That's the goal today. So an example would be to consider the two entries submitted to the unusually large fruit contest. Unusually large. So they're looking for exactly that. So the question is, which will impress the judges more at the unusually large fruit contest? A watermelon with a 10-inch diameter or a strawberry with a 3.5-inch diameter? Well, you can see to the side here that a 10-inch watermelon is perfectly average in relation to watermelons, having a z-score of 0. Perfectly average size watermelon, right? Because they're not asking which one's bigger. They're asking which one is unusually bigger, which means compared to the average, right? We're looking for high z-scores where a 2-inch diameter strawberry is average, so 3.5, that is almost double the size of the average. So that's a z-score of about 2.5. So the answer would be the strawberry. Okay, let's do some more comparing, this time in tables, looking at Joaquin's scores on his math and English tests. We're told these are from normally distributed test scores, so using the same formulas we've been using. And he wants to compare to ultimately find out which score is better relative to others. And we know that is a z-score, right? So he took a math test and English test and wants to see which one he did better on compared to others who took the same tests. And we would naturally assume the math test was harder because what's that number represent? This M here is just for math. These E's are for English. So the 70 here and the 76 represent the average, the mean score. So we could assume the math test is probably more challenging because of the lower average. Well, that's good to know. It's helpful to just think about everything that's going on. But ultimately, what we need to do is compare the z-scores. So let's solve for math first. Z-score is raw score. We see that at the top, right here, minus the mean over the standard deviation. We get 4/8, which is 1/2. Z-scores we prefer as decimals. Okay, slightly above average. And now English. Z-score again, raw score, mean, standard deviation. We get, let's see, 8. Not 8. Let's see. We get 12/10, I believe, which gives us, as a decimal, 1.2. Okay, let me check if I did that correctly. Oh, I got this one incorrect. Or did I? Let's see. 86 minus 70 for 8s. Something was entered incorrectly. Oh, that should have been 16. We solved that too quickly. 16/8, that's more like it, to give us 2. So subtract carefully. I almost made that mistake. Math was a better score overall, higher z-score. I'd say you did pretty good on both, still above average. And let's do the same thing, different situation, table of values. This will be a good chance for you to practice on your own. Okay, compare the data sets using z-scores. Sugar content in a soda is normally distributed. A serving of soda A has a mean sugar content of 39.2 grams, standard deviation of 0.4 grams. Okay, and then they go on to soda B. Let's focus first on soda A. They already asked for the z-scores, so we know we're using that formula. What do we know so far? They gave us the mean and the standard deviation. Okay, that's all they gave us so far. And then z-score for soda B. We have a mean of 40.6, standard deviation of 0.2. That's as far as we've got. Let's see what they want to know. They tell us Jamie's serving of soda has 40 grams of sugar. And they want to know, Jamie wants to know, which brand, soda A or soda B, is more likely to have 40 grams of sugar. So what's 40 represent? The raw score. Okay, so we work these out. And what happens? Let's see. Subtract. Divide. We get 0.8 over 0.4. That's a z-score of 2. And we get negative 0.6 over 0.2, which is -3 on the z-score. We did the work, but what's the answer? Well, they want to know which soda is more likely to have 40 grams. We plugged in the raw score of 40. So what we're really looking for is the closest z-score to the average. That would be soda A. And finally, our exit ticket. Suppose that scores on a biology test are normally distributed with a mean of 85 and a standard deviation of 4. Scores on history tests are normally distributed with a mean of 85 and a standard deviation of 2. On which test would a score of 87 be a better score? Explain. Was it A, B, or C? Let's take a look. B, the answer is history. We're finding the z-score for biology and z of history. Really, you're subbing and solving. You're collecting the information from above and plugging it in below. For biology, mean of 85, standard deviation 4. Scores on a history test normally distributed with a mean of 85, standard deviation of 2. Which test would score of 87 be better? We're plugging in 87s. And now we're looking for which score is higher. So it's important to pay close attention to what they're asking. Here we're looking for which fruit has the highest z-score. Here we're looking for, again, which has the highest z-score. Here was which z-score is closer to the average, the mean, z-score is 0. And here finally, which one would have a better score? So higher z-score once again. And that concludes this lesson. See you next time.